Alright, day 2. So here we're going to look at section 5.2 and 5.3. We're going to focus mainly on 5.3, which is the first derivative test, which is an incredibly important part of calculus. But we're also going to look at what's called Rolle's theorem, which is basically just common sense. So first we'll look at Rolle's theorem. Alright, so Rolle's theorem says if f is continuous on the closed interval a to b and differentiable on the open interval a to b, if f of a equals f of b, then there is a c, some point, in between a and b such that the derivative of c equals 0. That should make sense. So if you look at, this picture I have here, so this point and this point have the same y value, therefore somewhere in between there has to be a slope of 0. So there the derivative would equal 0, and here the derivative would equal 0. Even if the function is a horizontal line, this still holds true. So as long as it's continuous between a and b, if f of a equals f of b, then somewhere in between there the derivative has to equal 0. Again, that should be kind of common sense, or should just make sense. Alright, so now some more definition stuff. So f is increasing on an interval if for any two numbers, x1 and x2, in the interval x1 is less than x2, implies that f of x1 is less than f of x2. So that's our definition of increasing. F is decreasing. And remember, we actually did these definitions in first semester. So f is decreasing on an interval if for any two numbers, x1 and x2, in the interval x1 is less than x2, implies that f of x1 is greater than f of x2. And f is constant on an interval if for any two numbers x1 and x2, in the interval x1 is less than x2, implies that f of x1 equals f of x2. Again, these should not be new definitions to us. Okay, but understanding those definitions of increasing, decreasing, and constant leads us to a theorem which states given f is a function that is continuous on the closed interval AB and differentiable on the open interval AB then if the derivative is greater than 0 for all x in the open interval AB, then f is increasing on the closed interval. If the derivative is less than 0 for all x in the open interval AB, then f is decreasing on the closed interval AB. And if f prime of x, or the derivative, equals 0 for all x in AB, then f is constant on the closed interval a to b. So real quick, let's talk about what does this mean, because again, that's a lot of writing and seems fancier than what it really is. So if the derivative is positive, the function is increasing. That should make sense, because what does the derivative represent? The derivative represents the instantaneous slope of the function. So if the derivative is positive, the slope is positive. If the slope is positive, the function is increasing. If the derivative is negative, the slope is negative. If the slope is negative, the function is decreasing. If the derivative is 0, then that's a horizontal line. The slope is 0, so the function would be constant. A function is strictly monotonic on an interval if it is either increasing on the entire interval or decreasing on the entire interval. So basically, if it's increasing the entire time or decreasing the entire time, then it's what we call strictly monotonic. It is not monotonic if there's a constant interval in between. So for example, if you have, something like this, where in here it's constant. So this would not be considered strictly monotonic. Okay, so understanding all this increasing and decreasing stuff leads us to the first derivative test. So given f is continuous on an open interval I containing C, C is a critical number of f on I, so on this interval I. F is differentiable so the derivative exists on I, except possibly at C. So it doesn't have to exist at C. That's okay. It could, but it doesn't have to. Then, if the derivative is less than 0 on the interval to the left of C, and the derivative is greater than 0 to the right of C, then f of C is a relative minimum. And so let's talk about what that means. Well, if the derivative is less than 0, then the function is decreasing. If the derivative is greater than 0, then the function is increasing. So if it's decreasing to the left of the number and then increasing to the right of the number, that meant that it was going to be a minimum. If the derivative is greater than 0 on the interval to the left of C, and the derivative is less than 0 to the right of C, then f of C is a relative maximum. Again, that should make sense for the same reason. If the derivative is greater than 0, the function is increasing. and then the derivative is less than 0, so the function is decreasing. So if you go from increasing to decreasing, then you turned at a relative maximum. And then the last one, if the derivative does not change sign at c, then f of c is neither relative minimum nor relative maximum. And so again, remember back in the definition, c is a critical number. So critical numbers are where relative minimums and maximums occur, but they don't have to be where they, let me rephrase that. If a point is a relative minimum or maximum, it is a critical number. Just because it's a critical number doesn't mean that it's going to be a minimum or maximum. Okay, so let's look at some pictures of examples again, just to make sure we understand the idea of relative extrema. So let's just make up a picture. Let's say this is -1. I'm going to call this A. I'm going to call this B. I'm going to call this 4. And let's say we've got something like this. So I would have, in this case, I would say a critical value at A and B. This point here would be a relative max. This point here would be a relative min. Because this is an open interval, this point is going to be nothing. Because this is an open interval, this point here is also nothing. Those are not absolute maximums or minimums. I could also say this function is increasing from -1 to A, and from B to 4, and remember increasing and decreasing from first semester, decreasing from A to B. So this is just an example of relative extrema on an open interval. So let's look at absolute extrema. So again, let's just draw another picture. Let's call this 1, A, and 3. So this would be an open interval. I would have a critical value at A. This would be nothing, this would be nothing. This point here would be a relative and an absolute minimum. And here we can see we're increasing from A to 3, and decreasing from 1 to A. Okay, we're going to stop this video here. We do have a couple of examples for the first derivative test that we haven't gotten to yet. There's 3 examples, so that'll be in part 2.